Okay, so I'm going to make a start. So today we're wrapping up the rest of multithreading, and so it feels like it's been ages since we last had a lecture. But in the previous lectures, so in week 9, we introduced multithreading, and particularly the Monday lecture, we gave quite a bit of an overview of just multithreading in general, the ideas of basically starting up threads, shared memory, local memory, mutexes, deadlocks, race conditions, all that sort of stuff. And then we looked also in that Monday lecture last time on how to create some threads. And then in the Thursday lecture we looked at how to handle mutexes and lock guards and things like that. And this week in the tutorials, although given Labour Day happened, only one group of people have had tutorials so far, we have looked at having some code, so it's Mandelbrot set, and so that was just some code that is available online. And the Mandelbrot set is a big image, and you calculate each pixel, and each pixel is a mathematical calculation, and it doesn't depend on anything else other than its own value. So how can we multi-thread that piece of code? And so this week's tutorial, all for the guys who lost their Monday tutorial, that will be Monday next week. There's lots of different ways in which you can look at multi-threading that and splitting that problem up, and how you choose to do that. In that small-ish example, you won't see that much of an improvement, but again, if you scale these things to quite large systems, the differences really become dramatically different in terms of timing and things like that. During the break, assignment 4 was released. Assignment 4 is creating a parallel bucket sort, and you can read that spec on the course website. There is a PDF that you can request, which is a scan, a 6-page scan from a textbook on parallel programming, which will give you the ideas of what you should be thinking about on how to solve that. It does not give you the solution. It's written towards a language or a way of programming called OpenMPI, which we are not using. We're using advanced C++, C++11 threads and things like that. So you need to take the ideas from that and apply it to what we're learning in these lectures over the previous week and today's stuff. So today we're looking at the producer-consumer problem, and we're going to look at how we can communicate between threads. The stuff we're covering today, you may choose to use in your assignment if you want to, assignment 4. However, this stuff isn't strictly needed for assignment 4, but if you want to use it, you can. Okay. So who's heard of producer-consumer problem before? Most people. Yep. Cool. So producer-consumer problems like this. We have, for instance, a manufacturing plant. Okay. A manufacturing plant consumes materials. Okay, so it consumes materials and it produces products. So it's both consuming and producing. Okay. Now, our manufacturing plant might have limited storage for both the raw materials and the final products. So our manufacturing plant might have a limited amount of storage space for how much raw wood, nails, things like that it can take in. And it might also have a limited amount of storage space for what it can store when it's produced things. So for instance, if you're making bookcases or tables or something like that, there's only a limited amount of space you can store that before somebody has to come pick it up and take it away before you can produce more things. And you might have a situation about trucks deliver some raw materials to the plant, okay, and they arrive at random time intervals. So we might know that there's a couple of trucks coming today, but we're not quite sure when they're going to show up. Okay? Forget about trucks for a second, talk about a web server. A web server, exactly the same thing. You don't know when someone's going to come and access your web server. And if too many people come and access your web server at once, they're going to have to wait to get a free socket to then come and get the data out of your web server. Okay, so producer-consumer problem is not just about trucks and manufacturing plants. It's about any sort of service where you've actually got things coming in and you're sending things back out. Now, if there's no space in the plant for any of these trucks to arrive to drop off their raw materials, they have to wait for space to become available. And we hate waiting. Waiting slows our program down. Now, in addition to the trucks delivering the raw materials, we have some trains. Trains remove the final products from a plant, and these trains are nice. If there's no products to be taken away, they just wait until one's manufactured. Again, this is less than ideal if they're having to wait because they want to basically turn up and be loaded and go as quickly as possible. So we're trying to minimize waiting. That's what we're trying to do. We're trying to minimize waiting. Okay? Everyone clear on what this problem is? Okay? So, let's look at some code. Here's my manufacturing plant. My manufacturing plant is just a class. And what it's got is it's got a materials count. And so this materials count is just a count of how much raw material I have, okay? So in a more concrete example, this would be the amount of wood or the amount of nails or whatever, but for the case of simple toy examples, we just have a counter, okay? And of course that raw materials count has to be greater than 0 because we can't have negative raw materials. So if you really want to get tricky, that should be an unsigned int, not just an int, but it doesn't matter. We have a mutex for modifying that raw materials count. As you can imagine, when something gets delivered, so when the trucks come and deliver products, that raw materials count goes up. And when we produce something, that raw materials count goes down. And so there's a mutex on top of that controlling that. Okay? And we have a constant capacity. So if the capacity is 100, that means that we can't store more than one, materials can't exceed value 100. Okay, so we can't store more than 100 things in this manufacturing plant. We then have two functions. We've got a function called receive materials, which takes in an int I. That int I is the amount of materials it's receiving. As you can probably guess, that means that that int I increases materials count by that I value, so trucks coming in can be of different sizes. However, the function produce product doesn't take any parameters in. Produce product consumes 10 raw materials, so it decreases the count by 10. Okay, the screen on the right hand side has more of the code up as well. We of course have a constructor that constructs that materials count to initially be 0. Okay, that's a manufacturing plant. Here's our truck and our train. The truck is a class. The truck is associated with a manufacturing plant, so it has a reference to the manufacturing plant object. It's got a function inside it called deliver materials. The truck deliver materials just simply calls manufacturing plant's receive materials. And what it does is it delivers, so it's a little bit weird because the truck's delivering but the manufacturing plant's receiving. It delivers 10 raw materials. Again, if we're doing this more complex, we can change these values. And we have a train. Remember, a train is taking materials away. Again, it has a constructor that takes the manufacturing plant it's taking things away from. And the train has a function called get product. Get product calls the manufacturing plant to produce the product. Okay. That is the overview of how this thing works. These trucks and these trains having their direct references to the manufacturing plant might just seem a little bit odd. There is better ways to design this. Okay, we're trying to keep the example small. And one of the issues that we have, and we will get to, is we don't have in this sort of library, so C++11 threading library, any sort of explicit communication between threads. So particularly message parsing. So if you already know some multi-threading, particularly MPI type stuff, MPI you might structure this a little bit differently. The truck might send a message to the manufacturing plant, and the manufacturing plant might receive that message and respond. Okay, we're not doing that because just this code structure doesn't allow us to. Okay, but we have three things: we have our manufacturing plant, we have our truck, we have our train. They can all interact with each other. We clear so far? Yep. Okay. So let's take a look at how the manufacturing plants receive and produce functions look like. So our receive materials function, remember we have this materials count mutex. Back in our 2 slides before, we had that materials count mutex, which protected that materials count from being incremented or decremented at the same time as both receiving and producing. So we wrap that mutex in a lock guard. Okay? And so when you come in to receive materials, that mutex gets locked, or if it's already locked, it waits until it unlocks and then locks at that point. Now we go into this receive material, okay? And say if the plant is already full. So we haven't produced anything, we've received a whole ton of stuff, we've got already our capacity, remember it was 100 items, and we're trying to stick more stuff in, okay? And we said before the rules of this factory were that if the factory is already full, the trucks have to wait, okay? So somehow in this red section here, we have to wait for the capacity to happen, okay? Somehow in that sequence there, we have to wait for that capacity to happen, okay? Once that capacity becomes free, materials count, well, we plus equal it by that I value. The same applies to producing a product. We have lock guard around the mutex, okay, so it comes in, it locks. We then have a material count minus 10 because we said that producing a product will cost us 10 raw materials. Now, if the materials count, so the raw materials already available in the plant is less than the amount that we're going to be able to consume, we're going to have to wait for more materials to arrive. We can't go into a negative amount of materials. That doesn't make any sense. Okay? So same situation as above. We have to wait for materials to arrive. Okay? Once we've waited for materials to arrive and we've got some, then we can do 2 things. First of all, we can decrease our materials count, and the second thing is because this thing's producing something, well, we return what we are producing. Again, toy example, we're just returning 10, but if you're actually producing some sort of object, say this was a web server, and your producer and your consumer was a PHP scripting interface, and so the requests come in saying generate this page. What comes out at the end of it is a PHP parsed HTML page. Comes out of it, exactly the same idea. Okay, so the problem we've got is how do we release the lock in these circumstances and wait for either the capacity or the materials? How might we do this? I know 2 ways of doing this, but how might you do this? It doesn't have to be C++, just hand wave a little bit. What are the ideas of how we might do these waiting?
Release it and then sleep for a little while.
Okay, so your solution, and it's one of the solutions, it's not the best, okay? But the way in which you might traditionally approach this is you find a way to release the mutex, you sleep a while, you lock the mutex again, okay? You lock the mutex again and you see if we can continue, otherwise you sleep a little bit, wait again, okay? Now this is what's called busy waiting, okay? Basically, you're just going, oh, well, I'm going to sleep for 1 second, 10 seconds, okay? Now, particularly if you sleep for 10 seconds, not only are you doing nothing for 10 seconds, something could come in after that 1 second period and you've just wasted 9 seconds. Having said that, if your sleep is only 1 microsecond, you're going, oh, nothing, go to sleep, oh, nothing, go to sleep, oh, nothing, go to sleep, and you're constantly waking up checking if something's come in, and that checking for something's come in is also now not just, you've solved the sleep problem, but now you're just smashing the CPU, constantly checking if stuff's come in. Okay? So it is a solution, it's not the best solution. How else might we do it?
Same
Wait for signal. You've done multi-threading before, haven't you?
Yes.
Yes. Okay, so what we're working towards is waiting for some sort of signal. Okay? And that's what we're going to look at. So we're going to look at a thing called condition variables. And condition variables are a type of semaphore, if you have done multi-threading before. And condition variables allow threads to block, release a mutex. So remember, in the previous slide, we had the problem that mutex got locked. So we've got a block, we're going to release the mutex temporarily, and we're going to wait until the data is set by another thread or a time period has elapsed. Okay? So we're going to wait until there's data or some sort of timer has timed out. Now, I just said right at the start that we hadn't looked at any sort of inter-thread communication. Well, this here is a form of inter-thread communication. So how we use these condition variables is we create a thing called a standard condition variable down here. Okay? And so when we need to check or to wait for a condition to be true, we call wait, so a function called wait on the condition variable object. Okay? And if we need a signal or communicate that some data has been made available, we need to call the functions notify1 or notify all on the condition variable. Now, notify1, just there can be multiple threads waiting on the same condition variable, so notify1 will, of course, notify just one of those things that are waiting. Notify all will notify everybody. Okay? You can also think of this, again, historically this has come actually from the idea of trains, okay? And train signaling. So a train is going along a track. And two tracks are about to merge. At the junction of those two tracks, there's a big signal. And the signal is either currently it's like traffic lights controlled. It's red, orange, or green. And red, of course, means stop. Orange means caution, go slow, and green means you're fine to go. More historically, in terms of before that, they had these big arms that sort of raised or lowered to tell you to stop or go. Okay, and the whole idea of these semaphores is so that only one train can enter a particular track at a time, because if multiple trains on the same track at a time, well, they can physically collide with each other. It's exactly the same idea here. You have a situation whereby you're trying to protect a piece of code. Potential problems could happen, so you're trying to find a way to communicate when it's safe to proceed. Okay, so we have our condition variables. In this case, we're going to put in two condition variables. Okay, we have a condition variable called has materials, which we use to signal when new materials have arrived. And we have has capacity, which we use to signal when there's capacity available in the factory, in the manufacturing plant. So one way in which you could do this week's tutorial, which isn't in this week's tutorial, but who's done this week's tutorial? How many people? Okay, about 3 of you. Okay, that's exciting. So this week's tutorial, right at the very end, we set up a job queue. And basically, as threads become free, they take things off a job queue. And in order to achieve that, we have a recursive lambda function, which is exciting because recursive lambdas are different. You know, we can do cool things with lambdas. But another way in which you can do this week's tutorial is you could have some sort of condition variable that you signal saying, hey, I'm completed, give me more work to do. And you can use these signals, these semaphores, to go back and forth between stuff. It might actually slow things down. Any of these things to do with mutexes and locks and condition variables are designed to prevent problems like race conditions and deadlocks and stuff like that. But every additional piece of data or objects or locking or waiting you put into your code actually slows your code down. So it is a trade-off. You have to think about this, and this is part of assignment 4, is thinking about what is the fastest way to sort these items. There's multiple different ways of doing assignment 4. Okay, so coming back to talking about producer-consumer and these trains, these condition variables. Here is, okay, so we've got 2 slides back, we had these to-dos. Okay, we had these to-dos on 2 slides before. We come forward. This is for to-dos sorted out. Okay. We have a manufacturing plant that we've put for condition variables on. Okay, so the condition variables for trains and the trucks have nothing to do with these condition variables. Okay, the manufacturing plant itself is the one that's managing these condition variables. And so when the manufacturing plant receives materials, when manufacturing plant receives materials, then, like before, it gets the, oh, there's a difference. Before we had this lock guard, now, at the very end of the Thursday lecture 2 weeks ago, we talked about unique locks very briefly, okay? So, first of all, the lock guard is gone. We have this thing called a unique lock. It's a different form of a lock guard, okay? Basically, a default lock guard. Once it's locked, you have to go out of scope before it gets unlocked. A unique lock can be locked and unlocked in a different manner. Okay, so we swapped out our lock guards for our unique locks, but we're still wrapping the same mutex. Okay, now this receive materials. Now we've got to go use this condition variable that we created. So has capacity dot weight. Okay, so the condition variable has capacity. We're going to wait on a signal to this condition variable to say it actually has capacity. Okay. So we're waiting on this. We're giving that lock guard or that unique lock into the wait function there, so it knows to lock or unlock it. And then we have basically something that's going to be true or false. Something's going to be true or false to tell us if we should proceed, basically, if we should proceed. Okay. Now in this case, we've given it a lambda function. Okay. So given it a lambda function, and what we're saying is, if the materials count plus I is greater than capacity, okay. So if we're trying to receive materials, and what we're going to receive is going to exceed our capacity, return false, keep waiting. Okay, because we don't have capacity at the moment. Okay, but if that's not true, then so if we have space, then return true. Okay, so that's the condition that we're trying to satisfy. Again, these are why these are condition variables. So there's some sort of condition, some sort of true-false thing we're trying to satisfy. Okay, so we're going to keep waiting until we satisfy this condition. So we're going to keep waiting until the materials count plus the thing that we're trying to add in there's room for it. Okay. Once that proceeds, then we can continue like before. Materials count plus equals I. Okay. And then after we've received materials, we then send a signal. We send the signal to the second condition variable. Remember, we've got two condition variables. One is has capacity, one is has materials. We send the signal to the has materials condition variable to say we have materials in the factory. Because we're going to get into it, that condition variable might be waiting for us to receive materials. So once we've received materials, we send the signal, we say we have materials. The same applies for the produce product function. It's just the opposite way around in terms of those condition variables. Produce product, same as before. We have this unique lock. Okay, last time was lock guard, same difference. We've got this unique lock. We then say has materials dot weight. And so has materials dot weight. Again, we pass in that lock guard there. If the materials count is minus the amount it costs us to produce the object, it's going to be less than we've got in our manufacturing plant, return false, else return true. We keep waiting. Okay, so say if we're in this has materials wait loop here and we don't have enough materials. We're just going to stay blocked on this line. Okay, we're going to stay blocked on this line until we receive some stuff and this has material.notify1 gets called, and then we become true and we keep going. So this receive materials and this produce product functions are talking to each other through these condition variables. Okay? This is much easier and cleaner and going to be less it's going to be more bug free than you attempting to create a function called receive materials, create a function called produce product, create, say, a built-in value yourself and a mutex on a built-in value that says I have stuff, and have something lock that, and then set it and unlock it and busy wait and do, you know, all the drama we had with the first suggestion with all that busy waiting. This nicely cleans all this up for us. Okay? So condition variables are pretty good at being able to do this inter-process communication, to be able to send, hey, something's happened, I need to tell other people that some event has happened. Is it clear? Yep. Now, is there still a problem? Is there still a performance problem doing this? Okay, so there's no problem with the code, this is the correct way of doing it, but is there still a performance problem?
If we have multiple produced containers, the one we notify might not be, so one might try to take more materials than we currently have, even though we have some materials, we're notifying one.
Oh, no, that would be a bug in your code if you had that happen. Okay. So no, if you have multiple producers and consumers and one's consuming too much, yeah, that's a bug in your code.
I mean, like,
okay?
you call notify one, and if you have different consumers that consume different amounts, you might notify one that you're telling.
Yeah, that's what I'm saying. This is a bug in your code.
Oh,
okay. This would be a bug in your code. That's not what I'm going with this.
Okay.
Okay. Can anyone else think of? Think about this very carefully. Think about this very carefully. I have this situation about trains and trucks are coming up to my factory, and if something isn't happening, they have to wait. For receive and produce, I have to wait. What don't we like doing? We don't like waiting. So we're waiting. This is less waiting than for other examples that we've had, but we're still waiting. Okay, so we've looked at solutions that prevent deadlocks, we've looked at solutions that prevent memory corruption, but we're still stuck with this busy waiting problem. And busy waiting literally wastes time. And so the question that we have is, how can we make our code asynchronous and minimize waiting? How can we do this? Again, everything about multi-threading is all about performance. How quick can we go? If our train finds it has to wait for a product to be manufactured, okay, so our train finds, arrives at the station outside the factory and finds that it has to wait for a product to be manufactured, how could we set it up so it could go and collect another product from a different manufacturing plant and then return to the first at a later period? That is what we want to do. Okay, because we're going to minimize busy waiting. Yes, we're probably still wasting some time because that train's had to travel to that plant and gone, oops, there's no room, okay, I've got to trundle off somewhere else. So there is still a little bit of performance loss there. But imagine at a plant, it might take half a day to produce a product. That waiting for half a day is pretty terrible. Okay, now that's a pretty big exaggeration, but this busy waiting, it literally is terrible. We want to find a way to minimize it as much as possible. Okay, so again, let's talk high level. Let's not necessarily strictly talk C++, but how might we achieve this? How might we achieve this if the world was nice? Okay, if the world was nice, because this probably again wouldn't work in a real life situation, but if the world is nice and you go to it's Boxing Day. It's Boxing Day, and you go to JB Hi-Fi because they've got a pretty good sale on. Okay, they go to JB Hi-Fi because they've got a pretty good sale on, and you want to buy something. I don't know, a game, DVD, doesn't matter. Anyway, you want to buy something, and there's a huge queue at the cash registers. Huge queue of cache registers. Now, it's maybe approaching 5 o'clock or something like that. And you also want to go, I don't know, next door to Maya and buy some shoes or something like that. Okay? In an ideal situation, how would you resolve this thing of you've gone to JB Hi-Fi, and there's this massive queue, and you still want to buy that thing there, but you don't want to spend that time wasted in that queue. Okay? You don't want to waste your time standing in that queue. Instead, you want to go off to Maya and buy your shoes from Maya, and then come back to JB Hi-Fi when the queue is shorter. How might you do this in an ideal world? They tell you when to come back. They tell you when to come back. So the reason why I'm saying ideal world is because in real life, you would go, oh crap, that queue's like an hour long, stuff that I'm going to go put the DVD back, I'm going to go to Maya, I'm then going to come back. And when I come back that second time, I might still find the queue is an hour long. But in an ideal situation, we probably just want to put our name onto some sort of literal wait list, and when we come back, we get told, oh yes, you can jump back into the queue where you were, or the sale has been processed and here's your goods waiting for you to collect. Okay? So that's an ideal world. How might, oh, actually not how much, we're going to explain how we might do this with C++. So does everyone get that idea? We're trying to go, okay, we're waiting for this thing to be produced. We want to tell the manufacturing plant, hey, I want this thing produced, okay, but you haven't produced it, so I'm going to go off to, okay, I'm a truck driver, and I've got a busy day. I don't want to be waiting all day for you to produce me some Coca-Cola. I'm going to go off to a Pepsi factory first. I'm going to pick up my Pepsi from Pepsi factory, and I'm going to come back to you where you produce my Coca-Cola. Okay, that's what we're trying to do. So we've got two ideas going on here. We've got a function called standard async, and we have a function called standard future. And so this starts to get very complex at this stage. Okay, so just a heads up, this starts to get very complex. I don't expect you to do this for assignment 4. I think if someone did this for assignment 4, it would be pretty cool. I've been tempted myself. My assignment 4 doesn't do this. I've been tempted myself to sit down and do my assignment 4 this way. But it could be fun. It could also be a disaster. So probably don't start doing your assignment 4 this way. But okay, so we've got this thing. It's called standard async. And standard async creates a thread. Okay, creates a thread to go off and do some stuff. And it returns this object called a standard future. And a standard future is what stores the result of the thread. Okay? And it can work entirely without shared memory and mutexes. So again, it's really unfortunate where the semester break has fallen, because you've probably forgotten everything from 2 weeks ago. But 2 weeks ago, when we're talking about threads and talking about shared memory and things like that, one of the things that we couldn't do is we couldn't start up a thread and have the thread return some sort of value. Instead, we had to start the thread up. We'd have to write something into some sort of shared memory and lock it with a mutex and all that sort of stuff. Okay, so this is different. This thing starts up a thread, allows us to maybe calculate or produce something and have it get returned to us wrapped in this standard futures object. Okay. Now, standard async hands control of when to start a thread to the runtime system. So it may not be called immediately if the system is busy. What that means is we call standard thread, and a thread gets generated immediately. And again, computers are very fast these days, but you know, my laptop in front of me here has 8 cores. Okay, my laptop in front of me here has 8 cores. Something that's really dumb, and do not do this in assignment 4, is with a parallel bucket sort, for instance. With parallel bucket sort, one idea you might have is, hey, I'm going to start up 10 threads for 10 buckets. It's a bit of a dumb idea because I've only got 8 cores. And so what happens is, on the kernel level of the laptop, or the kernel level of the Linux system, or Windows, or whatever system you're using, because you're trying to do more than it has space available. It literally gives a little bit of time to the first process, and then goes, oh, you've had enough time, I'm going to just pause you, push you off to the side, dump all your memory off that way, and this other process can come in, it can use a little bit of time. Oh, your time's up, I'm going to bring that first one back in and keep going. You've got a lot of these switching, it's called context switching, between bringing that application first of all onto a CPU and bringing all that memory into space and then pushing it back out. So ideally you shouldn't exceed the number of threads for the number of cores you have available. Okay? So you shouldn't exceed that limit. And again, with assignment 4, I am giving you the number of threads that you should be starting, and you don't have to adhere to that. You don't have to adhere to that. My strong recommendation is you do. And one of the things I might do when marking it is, even if we run this on an 8-threaded system, I might only tell you you've got 7 cores available. And it's pretty standard practice to not give you complete control over the entire system. It's pretty standard practice to only give you, say if there's 8 CPUs, only 7 or 6, or maybe even 4. The reason for that is if I've got 8 CPUs and I give my program all 8 CPUs at once, has anyone ever done this in terms of running some code? What happens if you run a process, particularly a long running process? So say Mandelbrot said, I ran it for a day on a huge image, took me 4 minutes to calculate. What would happen to my system if I consume all 8 CPUs for 4 minutes on the same process? What would happen to my system? Do you want to know?
Does it get really laggy with your context switching between the OS GUI and process, or will it just hang because it's actually in the process the whole time?
Okay, it shouldn't hang. It can. It shouldn't hang, but the first answer was the correct answer. Remember, the rest of my operating system needs to keep going. If the rest of my operating system is running my GUI, my mouse inputs, my network connections, if I actually, okay, I'm going to load up my terminal here. If I load up top, what I'll see is, at the moment on this computer, I have 372 processes running in the background. 369 of them right at this second are sleeping. Okay? But there's a lot of other stuff that's going on your computer in the background. And the same applies to the school systems. I am not going to go crash for school systems just to run your assignment 4 marking. Okay? So what's more than likely I'm going to do is I'm going to give you some value that's less than the number of actual CPUs available. Okay? This is about standard async becomes helpful. Oh, okay. Assignment 4, you should adhere to that limit and probably follow what we did in tutorials this week, or if you haven't done it this week, coming, whereabouts we created a vector of shared pointers over threads, and you basically keep those number of shared pointers, or those number of threads within that limit. So you can tear them down, you can start them up. But in the context of standard async, this is the point. Standard async can when it hands the control over to the runtime system will look at your system usage and work out, hey, should I go produce this thing now? Or, hey, if the system's too busy, should I wait some time and find a time when the system is free? Now remember that standard async is returning this standard futures object, and the standard futures object, like I said, stores the result, okay? But as wrapped in this object, okay? So the standard futures object that gets returned, not for a result, the result gets into that, but for the standard futures object that gets returned, can be used to check if the result of that calculation that should be there is available or not. And so what we can do is we can, with our manufacturing plant, wrap our producer in a standard futures object, and the train comes in, and the train gets one of these standard future objects, because it goes, yeah, it's not available yet. Okay, cool, I'm going off to the Pepsi factory, or I'm going off to Maya or JB Hi-Fi, or wherever we're going, okay? And once he gets to Maya, okay, let's talk about Maya instead. Once he gets to Maya, he does this thing at Maya, and he's then able to look at the standard futures object, and he's able to go, has this thing been produced yet? Back at JB Hi-Fi, am I at the front of the queue yet? Maybe you can even think about it if you go to a bar or a restaurant and you order food and you get those buzzers. Remember you get those buzzers if you order food at a pub or a restaurant or something like that? And when your food's ready, they buzz and you go and collect your food. Everyone's seen those? Okay? Same idea. Same idea. Those buzzers, when you order for food, that buzzer is essentially your standard futures object. Okay? And when your food becomes available, it buzzes and you know to go and get it. Same idea. Okay? So here's an example sketch of how this thing might work. Okay? So this is not producer consumer anymore. Okay? This is just a sketch of how this stuff might work because this stuff is really quite new and quite advanced in terms of C++. I think C++14 has better support for it. Okay? But say we have a function up here, it's just called calculate. Okay, it's going to go off and do some crazy fun calculations. In case of this one, it's doing the most difficult calculation in the world. It's returning 1, 2, 3. Okay, but we've got this function called calculate. Okay, hey, that function actually might be Mandelbrot set calculation. You know, could be anything. We go into main and we call standard async calculate. Okay, now this standard async calculate call can do two things. As well as working out, I hate the screen source room. As well as working out when to, when it should spawn off another thread or not. Okay, it can also decide that maybe if the system only has one core, maybe it's so busy that instead of starting a new thread, I'm just going to find somewhere in the current call stack to jump in and just run it on the same processor it's already doing. Okay? Async's amazing. You're basically handing control over to something that is smarter than you are. Okay? Now, you can force it to use a new thread. You can force it to always go off and use a new thread by calling it in that approach like that. And the reason, again, why you might do that is maybe you're pretty confident in your code that you're going, actually, this code I'm currently running this code on, it's going to be calculating stuff all day long. I really need this to go launch on a different process. And you can tell it to do that. Okay, so what we've got is we've got this futures object that is the result of this async calculation that may or may not happen when we first call it. Okay? We have this while loop here of doing other work. Okay, so this is going to other factories. While we're doing other work, at the start of this loop, we're going to check if the result of this thing is available. Okay, so while future up there, while we're going to wait for no time, okay, we're just going to see if it's there because we don't want to wait. So while we're waiting for 0 seconds, if we're timing out, so i.e. the thing that's being produced is not available, we're just going to go off and do other work, e.g. go to a different factory. If it is available, then we're going to go collect it. And then, so we go off and do other work, we do some other work for a little while, maybe go off to a Pepsi factory, and we loop back around, and the thing is still not available. The thing is still not available, so instead of being at the Pepsi factory, we now go off to the juice factory. Okay, so standard futures, we can just keep on checking them going, is the food buzzer buzzing yet? Okay, what's going on? And then once we get out of this loop, okay, so my break and my loop is do other work if it's false, I break the loop. Down here I can get the result of that future. So remember I said the result of that calculation gets dumped into that futures object. Okay, so once the future isn't timing out anymore, once it's available, I dump the result of that into that variable there. Okay. Confused? Anyone completely confused? I don't care whether you understand the code or not, okay? There's no exam questions on any of today's material, okay? I don't care if you understand this material or not. Well, I want you to understand the high level of what's going on, okay? So that's why I'm talking about JB Hi-Fi and Maya and trains and all that sort of stuff, high level, okay? We've got 5 minutes. I've got one thing else to show you. So one of the other things that we had, and you may actually face this. You may actually face this one in assignment 4, depending on how you write your code. again, going back 2 weeks, we said that you can't throw exceptions across threads. If you start up a new thread and it has an exception and you don't catch that exception, well, your entire code crashes. Okay? Standard futures can throw exceptions across threads. It's less than ideal because, well, I just told you, standard futures, they don't need mutexes, they don't need shared memory or anything like that. So throwing an exception out and down some threads, it's kind of not necessarily the best idea in the world, but it's probably still better than your entire code terminating. So when you call the get function on the future, that almost sounds wrong. You may get the result that was calculated, or if that calculate function had thrown some sort of exception, you'll get the exception that was thrown. So we've modified the calculate example here, so instead of it's returning 123, it's just throwing a runtime error. Okay. And so what we do is we go modify our code. So we still try to get the result. We expect it to be an integer. We've wrapped this in a try-catch block. We catch the exception down here because that result, just threw in a runtime exception. And again, my laptop isn't up on the screen anymore, but there's an example of this. Actually, let me just jump to it. There's an example of this in the sample code that's available. That is essentially what you just saw on those slides there. So calculate is throwing a runtime error, and we've got the try catch, and it's catching that exception across the threads. Okay. So this brings us to the end of multithreading. It brings us to the end of multithreading. The last week and a half of material should give you lots of ideas for how to go do assignment 4. Assignment 4 is all about speed. All about speed. So I believe I've given you a struct to work with. I've given you a lambda function that destroy that lambda function. I don't want to see that lambda function, okay? Destroy the lambda function. The lambda function is awfully slow. Awfully slow. You can even write a better version that on just a single core, someone emailed me this morning and said they'd got it going on a single core 10 times faster than that lambda function goes. Okay? I checked my code. My code, I go about 6 times faster with just rewriting that lambda function on a single core, but that's not the purpose of the assignment. I know that lambda function is slow. Okay? The purpose of the assignment is to do multi-threading. You can use any and all the resources that we've shown you here. The only requirement with that assignment 4 is you have to maintain that vector. So that vector I dump information into, and then I pulled out the result out of that vector. It's in a struct, so there's no getters and setters. That sort function for header has to stay the same, but you can rewrite that sort however you like. You can put additional functions in. You can do whatever you like, basically, to get it going as fast as possible. The short version is fastest code wins. It's essentially what it is. Fastest code plus correct code wins. So that's due the Thursday of week 13. The reason why it's due the Thursday is it means the late penalties clear off by the time StuVac starts, so we can mark it as quickly as possible and get those marks due before the exam. Next week we're talking about object-oriented programming, and of course there's no assignments on object-oriented programming, but there is exam questions on object-oriented programming. So that's next week. One real quick final thing I'm going to talk about